So let's do some more examples of doing calculations and following the significant figure rules. So here we have two numbers, 6.74 and 2.9, and we're going to add them together. The rules say that when we add these numbers together, we want our answer to have the least precise measurement. For addition and subtraction, the least precise measurement is the one with the fewest decimal places. So 2.9 has one decimal place, and so our answer should have one decimal place. When we add these numbers together, we'll get 9.64. 9.6 is one decimal place. The 4 by rule tells us not to round up. So our answer here, 9.6. What happens when we multiply these numbers together? 6.74 times 2.9. Our least precise measurement is the one with the fewest significant figures when we're multiplying and dividing. Here, 2.9 with two significant figures has the fewest significant figures. So our answer should have the fewest significant figures, which is 2. So when we plug this in the calculator, we get 19.546. And so again, this is what comes out of our calculator. We want our answer to have two significant figures. So 10, right, 1, and 9, that's 19. So I'm going to draw just a broken line here to represent the two significant figures. Now remember, by rule, we use the following number to tell us whether to round up or not. In this case, 5 tells us to round up. So 19 gets rounded up to 20. But wait. By significant figure rules, the way 20 is written here is one significant figure. Why? The 0 is a trailing 0 without a decimal point. So that means there's one significant figure. Remember, we want our answer to have two significant figures. And so what we'll do here is we'll add a decimal place. And so now the trailing 0 with a decimal place is significant. So the answer here is 20 with a decimal place. Okay. Let's do another example. 0.029 divided by 6.74. So here we're doing division. Again, we want our value to have the fewest number of significant figures when we're dividing. 6.74 has 3 significant figures. 0.029 has 2. These leading zeros are never significant. So we want our answer to have 2 significant figures. When we plug this in the calculator, our calculator is going to spit out a lot of numbers. 0.004302671, and some calculators may even go farther than this. So again, this answer is not correct. By rule, we can only report the significant figures as our least precise measurement, which is 2 significant figures. So let's count. 0.00 are not significant. These are leading zeros. 4.3 is significant. 4.3 is 2 significant figures. And again, our next number tells us not to round up. So our answer is 0.0043. We can also answer this in scientific notation. So go to your notes and check out the explanation of scientific notation. Moving the decimal place over to the right 1, 2, 3 times, we'll have the decimal place after a non-zero integer, and this will be times 3 raised to the negative 3. So remember, negative exponents means that we're taking 4.3 and we're going to divide it by 10 this number of times. Okay, I got one more for you. Look at the example of 15.3527 minus 15.35. And so in this example, we've got two numbers and we're subtracting them. We want to know the difference. By rule, subtraction, we want the fewest decimal places. And the answer here is 0.0027. And we'll rewrite this. It's typical just to write 1 0 in front of the decimal place, so we'll leave it as 0.0027. Now, we want fewest decimal places, so we want 2 decimal places. 0 point, count the number of decimal places after the decimal, 0, 0, and the next number tells me not to round up. So this is interesting. In this example, the answer is 0.00. Now let's talk about that for a minute. Does that mean there's no difference between these two numbers? No. Obviously, you can see that there is a difference. Of course, this number reads few more significant figures, right? 2 more. This number reads fewer significant figures. We're more certain with the top number and less certain with the bottom number. If we were taking measurements here, we would say that we have more resolution in our instrument to read this top number, and we have less resolution for this bottom number. Does that mean there's no difference between the two? There is a difference between the two. But at least to 2 significant figures, at least to what we're certain of, the difference is 0.00.